Okay, a semi-infinite rod lies on the y-axis with one end at the origin as shown. The positively charged rod has a uniform charge density lambda. Derive an equation for the electric field at the point a, 0, where a is a constant, in terms of k, lambda, a, and appropriate unit vectors. So we want to find the electric field. So what we need to start with is we need to draw a dq. So let's just say dq is a slice right here, a slice of that rod. And we'll label that dq. Alright, so the length from dq to a, we'll say, is r. And the r goes from the source, dq, to the point, the field point. And that's obviously going to be a vector. So let's go ahead and label some more stuff. We can say that the distance from this point here to this point is y, and the distance from the origin to that point there is a. So now what do we do? Given now we have this, let's go ahead and start writing our equation. So we first start with the electric field integral. The electric field is equal to k times the integral of r, that right there, over r squared dq. Now, let's examine this picture here. The vector r has a different length for each dq, right? If dq was here, r would be different. Therefore, its magnitude r can't come out of the integral because it's not a constant. What you want to do now is express r in terms of a constant a and the variable y using the Pythagorean theorem, because we defined y and a to be the length, the side lengths. So what we do then is we just say r is equal to the square root of a squared plus y squared. Also, r points in a different direction for each dq that makes up the rod. So its direction r cannot also come out of the integral. But note that r extends a unit to the right, obviously, along the unit x, and y units downwards along negative y. So what you can also say is that r is equal to ax, where I hat x, minus y times y hat. So we want to find the unit vector r by dividing r by r, the vector r by r. So all that sounds kind of confusing, right? But we want to find this. In order to do that, you just divide the vector r by this, and so you get a x hat minus y hat over a squared plus y squared. So let me go ahead and rewrite the electric field integral so we have more space. So we have the electric field E is equal to k times r hat over r squared dq. Remember, so we can't integrate this, so let's go ahead and substitute. So let's substitute the expressions for r and r hat into the electric field integral. So we can now say let's just go ahead and write this. Bring out that r hat. And now you're left with 1 over r squared dq. And now we can go ahead and further simplify this. Let's go ahead and substitute r hat, which is up there, and we're going to write a x hat minus y hat all over the square root of a squared plus y squared times, note that there's two of them, times 1 over a squared plus y squared dq. Now, we're almost done with this part. So now what you're going to want to do is we can combine these. We just have a squared plus y squared to the power of 1/2 times a squared plus y squared. So we can just rewrite that as so the reason what I did here was r squared is equal to a squared plus y squared squared, which is just equal to a squared plus y squared. Alright. So let's go ahead and combine more. So we can say e is equal to k times the integral a x hat minus y hat over a squared plus y squared to the power of 3/2 dq. Alright. Now, so for a thin rod, dq is going to be equal to lambda ds. So let's go ahead and rewrite this further to be E is going to be equal to k times a x hat minus y hat over a squared plus y squared to the power of 3/2 times lambda ds. Now, since the rod has a uniform charge density, which was inside the question right here, we can pull that out. So that means that this integral will now become this. E equals k lambda times integral a x hat minus y hat over a squared plus y squared to the power of 3/2 ds. Now, for a rod lying along the y-axis, which it is here, you're going to work with Cartesian coordinates. And we're going to need a differential arc length. So, the differential arc length in this sense will be, let me move over here. The differential arc length will be this. ds is going to be what? Which axis does it correspond to? Well, it's going to be dy. Therefore, the limits of integration correspond to the length of the rod, and it's a semi-infinite rod. And all that means is just, when you're saying a semi-infinite rod, all that means is just A is much less than L, the length of the rod. So the distance A from the rod is much less than the actual length of the rod. At any rate, what we can now say is, because this is going to be an infinite rod, let's go ahead and look now at the limits of integration. So the limits of integration correspond to the length of the rod being 0 is less than y is less than infinity. So let's go ahead and write that. The electric field, E, is equal to k lambda times the integral from 0 to infinity of ax hat minus y hat over a squared plus y squared to the power of 3/2 dy. Now, let's split this integral into two integrals. So now we can say, let's just say this is identical to E is equal to k lambda times the integral from 0 to infinity of ax hat over the denominator a squared plus y squared to the power of 3/2 dy minus k lambda times the integral from 0 to infinity of y times y hat over a squared plus y squared to the power of 3/2 dy. That's it. So let's look at this. This is the equation that we're now looking at. Let me box that for you. Oh my goodness. Alright. So what next? Notice that the constant a can come out because we're not taking it with respect to a. And the unit vectors x and y also come out. So let's go ahead and do that. So we can now write that as E is equal to k lambda a x hat times the integral of 1 over a squared from 0 to infinity plus y squared to the power of 3/2 dy minus k lambda y hat times integral from 0 to infinity of y over a squared plus y squared to the power of 3/2 dy. Now, how can we solve this integral? Try to remember your trig substitution. We can say that y is equal to a tan theta therefore dy is equal to a secant squared theta d theta. Solving for theta, you get theta is equal to tan to the negative 1 of y over a. This also will imply that the new limits of integration are from, we plug them in. Theta is tan to the negative 1 of 0, which is 0 degrees, to theta equals tan to the negative 1 of infinity, which is 90 degrees. So, also remember that the denominator of this integral will simplify using the trig identity 1 plus tan squared theta is equal to secant squared theta. So, let's see. We have a squared plus y squared to the power of 3 halves, which is equal to a squared plus a tan theta squared to the power of 3 halves, which is equal to a squared plus, a squared times one plus tan squared theta to the power of 3 halves. And this is going to be equal to a squared secant squared theta to the power of 3 halves, which is simplifying to a cubed times secant cubed of theta. That's it. So now, let's go ahead and rework this integral. So now we can say that e is going to be equal to k lambda a x hat times the integral from 0 degrees, or we can say, I guess, theta equals 0 degrees to 90 degrees, of 1 over a cubed secant cubed theta times a secant squared theta d theta minus the second integral k lambda y hat times the integral from theta equals 0 degrees to 90 degrees of a tan theta, remember we set y equal to that, all over a cubed times secant cubed theta times a secant squared theta, d theta. Oh, Jesus. So, we can now simplify this whole thing to now be note that this secants cancel this and this cancel. Well, these don't necessarily cancel, but the numerator does. So let's go ahead and rework that just by substitution, or sorry, just by simplification. now you can say E is equal to K lambda A x hat times the integral from theta equals 0 degrees to 90 degrees of d theta all over A squared secant theta minus K lambda y hat times the integral from theta equals 0 degrees to 90 degrees of tan theta d theta all over A secant of theta. Now, if you need to take a minute to simplify that, just pause the video. Now, how can we simplify this further? Well, note that, here, let me go over here. Note that secant of theta is equal to 1 over cosine of theta, and tan of theta is just sine over over cosine of theta. So we have tan over secant, right? So all that means is sine of theta over cosine of theta divided by 1 over cosine of theta, which is equal to sine theta over cosine theta times cosine of theta over 1, which is sine theta. So now we can finally rework this and say E is equal to K lambda A x hat times the integral from theta equals 0 degrees to 90 degrees of cosine of theta over A squared d theta minus K lambda y hat times theta equals 0 degrees over 90 degrees of sine theta over A d theta. Now, we can pull the constant A out this integral. So if you pull out these, note that A over A squared is 1 over A. So we can simplify this further to be E is equal to K lambda x hat all over A, integral from theta equals 0 degrees to 90 degrees of cosine theta d theta minus K lambda y hat over A times the integral of from theta equals 0 degrees to 90 degrees of sine theta d theta equals, what does that equal? That's going to be K lambda x hat over A times 1 minus 0 minus K lambda y hat over A times negative 0 plus 1. Now that all simplifies to now be E is going to be equal to K lambda x hat all over A minus K lambda y hat all over A, which is going to be equal to K lambda over A times x hat minus y hat. Now, we're allowed to use lambda in our final answer because the question said you can use it. So you don't need to integrate q equals integral of dq. So the electric field at point A, 0 is E equals K lambda over A times x hat minus y hat. That is the answer.